Okay, welcome to our chapter 1 of our Precalculus class. This time we're going to be focusing on functions and graphs. This will be some sort of a review of our algebra class from last year, and we are going to brush through it and we're going to redefine everything that we have been discussing for the past year. Now, for the next one, we have these topics to tackle in this video, and the first one will be domain and range, and the second one will be increasing and decreasing functions. That's for part 1. And for part 2, we're going to be focusing more on local and absolute extrema, asymptotes and symmetry, and end behavior. Let's move on to the functions and notations. Okay, so think of a function as a machine. And think of it this way, like if you have a machine like this and we have something called an independent variable, or what we call x, let's put that into the machine, and once it's processed, it's going to spit out this something called a dependent variable, or the function of x. Sometimes we call it y, but usually whatever the value for x is will affect the value for y. So this is why we have this classic function y is equal to f of x, or as we read it as y as the function of x, or y is equal to f of x. This is called the Euler's function of notation, and this is very simple, very easy to learn, and it's used in all of math. You should be familiar with this by now. We use this a lot in our algebra class, and you're going to see this a lot through Precalculus and up to the calculus courses preceding this whole course. Let's define a function. Through this example, let's read, does the formula y is equal to x squared define y as a function of x? Resounding, this is going to be a specific. It's a yes, of course. But how are we going to do that? We have to digest it as it is. As we know from our previous algebra course, y is equal to x squared is the parent function of a parabola if you try to graph it. It starts at the origin at 0, 0, and it opens upwards. If we're going to look at this space at the side over here, the x and y plane, and we're going to plot the whole thing as points, you can see that the whole thing opens upwards, and for every value of x, there's going to be a y. And if you try to move across this from the left to the right, like say a vertical line test, you're going to notice that the line will not touch part of the graph twice. So that's how you define a function. One of the values that we need to understand about a function is that we need to define the domain and the range. If you understand the domain and the range, you're going to be able to predict what will be the value that will be acceptable for your graph or your function. So for the domain, the saying goes that the set of number for x that will satisfy the equation, which means that as long as it won't create an error in the value, then it is part of the domain. So basically, whatever your value for x is, it should not create any form of error or any form of mistake, or it should not lead to an imaginary number in your equation. Let's look at this example. Find the domain of f of x is equal to square root of x plus 3. Now let's look at this a little bit closely. So the domain needs to be a set of all numbers that will satisfy this equation. Okay, now let's look at this one. First, if you observe the function over here at the left, you will see that there is a square root. Now, if we have a square root, that means that the value of the radical must not be negative. I mean the inside of it. Because once you get the square root of a negative number, you're crossing over into imaginary number territory. And we don't want that for classical math. Now, if we are going to isolate the value inside the radical, x plus 3, and we equate it to 0 or greater than 0, then we should have an inequality that goes x must be greater than or equal to negative 3. The meaning of this is that if you try to put any number less than negative 3 into the whole radical, you're going to end up with a negative number. Like for example, if your x is negative 4, then obviously you're going to end up getting the square root of negative 1, which is an imaginary number, and it's not acceptable in this form. So in conclusion, this is the domain. So this notation right here When you read this, you're basically telling that the domain is all set of values greater than -3. The left side over here, the bracket, this indicates a specific number. So usually in this case, it's -3 because your graph or your function only allows a minimum of -3 for the x value. And it goes towards infinity. So when you notate the end part of this, it's a parenthesis. So when you have a parenthesis over there, it indicates a continuous number, which is in this case positive infinity. If we look further, if you try to graph the whole thing, the square root of x plus 3, you're going to end up with this half parabola opening to the side. But if you look at -4 over here, if ever your value crosses that number, if ever your x is equal to -4, that will be unacceptable because it's never going to be part of the function. So if your x is equal to -4, then y will be imaginary, which is something we cannot represent in this xy plane. Let's move on. Now for the range, there's a saying that any set of numbers for y that will satisfy the equation is very similar to domain. For domain, you're basically looking at the x values. For the y values, it's for the range. Let's go for an example. Find the range for f of x is equal to 2 over x. Now, the thing about this, it's a fraction and your x is in the denominator. If you consider the values for this one, we have to look at x first. We have to consider it. Because if we look at this, obviously the range for this one is, the domain for this one will be 0 to positive infinity, which means that y cannot be 0. So why is that the case? For any situation that your x becomes 0, you'll end up with 2 over 0, which is equal to infinity. And that is called an asymptote, which is something that we're going to discuss in a future video. Now, if your function ends up as an infinity or an asymptote or 2 over 0, that's a bit of an anomaly in the graph. Now let's try to solve that algebraically. Let's say we are going to equate y equals 0, and you're going to have this form. Then we cross multiply x into 0, so 2 is equal to 0 times x, and that will lead to 2 is equal to 0, which is false. That can't be. So obviously this is not a very this proves it that 0 must not be the value for x and the y. Now if you try to graph this as shown here, you will see that your function cultivates from the left to the right and from the bottom to down. But the difference is that if you point out the origin or the 0 here, or the x and the y axes, your curve will never touch them because the function doesn't allow it. So that's how this one goes. So which means that the domain and the range are all values except for 0. See there. Let's move on. So another part of us trying to define a function is whether or not they're increasing and decreasing in say their slope. In algebra, we have something called the slope, which is the rise over run of a function. It tells you where the line is going, whether it's increasing to the right up or it's decreasing to the right down. But if a function is increasing if the change between the 2 points are positive. So if that's the case, you have a positive slope and it's going up. Now, if you have a function that is decreasing, then the change between the 2 points are negative, which is defining a negative slope, if you remember that from your algebra. The next will be a function is constant if the change between the 2 points are 0. You're basically telling me that the slope is 0, or you're flatlining, or it's a horizontal line. Now we can look at that graphically. Let me show you in a bit. First, we have an increasing function here, or an increasing slope. Vaguely, this is not a line. If you look at it, it's obviously something else. But if you can see the general slope of the whole graph or the whole function, you can see that it's increasing from the right to the left and from the bottom to up in this direction. Now, if we have a decreasing function over here, you can see that there's a general slope going downwards. Now, if you draw a line, you can see where the trajectory goes. And next part will be the constant one. You can see that it's flatlining completely, and this is a zero slope, and this is a horizontal line. If you draw a line through it, obviously it's going to be a flat line like this. And for piecewise functions and continuous functions like this, there could be multiple slopes or different kinds of directions for say the graph of this function. Let's say from the left, it's starting as an increasing, as a decreasing, then it becomes a constant in the middle, and it becomes an increasing function at the end. This is probably a piecewise function or a different kind of function. But you can see that you can really define where the decreasing and the increasing part is just by looking at the graph. But what if you are not presented a graph? What if you're presented a value table like this? So let's find out. So first, we can see that the x's are basically the same. They're increasing from the left to the right over there, and it doesn't appear to show any asymptotes. So I assume this is a continuous graph from negative infinity to positive infinity. Now, if you look at the first table over here with the y1, you can see that all of the value for y are the same, which means when you try to get the difference between them, you're going to get a 0. This indicates that it's going to be a constant graph. But let's move on to the next table for now. Now, for the second table, you can see that the y2 varies differently. Now, if you look at the 1 and the 0 and you get the difference between them, you get a value of 1. Moving further, you're going to have a value of 2. Moving further, you have a value of 4 and 6. Okay, so this tells me if you look at the y now, it's actually decreasing and it's going down. While you are going to the right for x, you're actually going down for y. For the third table, it's obvious that it's going up due to the nature of the values from -5 to -10 as it goes up. So obviously from the first table, it's going to be a constant, and the next one will be a decreasing function, and the third one will be an increasing function. So this wraps up our first part of the video for the functions and graphs. And for the second part, we will be discussing more of the continuities and the other characteristics of functions.